Hello and welcome to Lecture 6 of Foundations of Artificial Intelligence. Today we're going to be introducing first-order predicate logic. In particular, we're going to be focusing on representation. Over the last two lectures we covered propositional logic, with our last lecture focusing on reasoning. In particular, we covered entailment, arguments, inference rules, and deductive reasoning from a knowledge base. Today's lecture will cover the question, what is predicate logic? We'll also talk about predicate logic syntax, predicate logic equivalence, and predicate logic semantics. Let's start by answering the question, what is predicate logic? Let's start by looking at this argument from Socrates that we've seen a few times before. It goes, all men are mortal, Socrates is a man, therefore Socrates is mortal. If we apply propositional logic to turn this into an argument like we've already learned, we get this argument formula. Taking a closer look at this argument, it doesn't actually make any sense. Here we're claiming that if P and if Q, then we conclude R. Clearly this doesn't make any sense. So what are we missing? Well, the validity of Socrates' argument comes from the internal structure of the individual sentences, which propositional logic can't see. This highlights a basic problem with propositional logic, and that is, it's not possible to write general statements as propositions. For example, a sentence like, Finn eats everything that he likes. To explain this in propositional logic, it would require us to enumerate all propositions. For example, in addition to Finn eats what he likes, we'd also have to include the foods that he likes, such as Finn likes cakes, Finn likes bananas, and Finn likes kale. Going back to Socrates' argument, would it be practical in propositional logic to enumerate all people in the world who are mortal? Of course not. So what do we need? Well, in essence, we need to split the atom. Or more specifically, we need to display the internal structure of those atomic sentences by adding new categories of vocabulary items to our logic syntax. We also need to give a semantic account of these new vocabulary items. And lastly, we need to introduce new rules for operating with them. So what's the biggest draw to using first-order predicate logic? Well, mainly it offers flexibility and conciseness. Ultimately, predicate logic makes general statements possible. Rather than having simple, concrete propositions, predicate logic allows for conditional and collective propositions. In other words, statements of existence and statements of number. This is essential for dealing with more complex problems or environments. First-order predicate logic goes by a number of names, including predicate logic, which we'll use mostly in this lecture, first-order logic, with the acronym FOL, quantification logic, and first-order predicate calculus. Predicate logic is an abstraction of propositional logic, but we're going to need to add some additional syntax. In particular, we're going to add the following things: constants, variables, predicates, functions, equality, and quantifiers, which will play a major role in today's lecture. As an analogy, let's say that syllogistic logic is like learning to count. Propositional logic is more like learning to do basic arithmetic. And that makes predicate logic like learning algebra. Each of these forms of logic are a progressive elaboration building on the one that comes before it. So what do we mean by first order? Obviously not this. The term first order basically distinguishes first order logic from other higher order logics. First order is simpler. For the purpose of this course, we're not going to dive into higher order logics. I bring it up here just so you're aware that they exist. Now let's dive into the new syntax that we introduce with predicate logic. First, let's introduce constants. These are invariable nouns. In other words, their value or meaning does not change. Constants represent objects, such as people, places, things, and times. For example, they could represent myself, Socrates, Ohio, Saturday, cake, and Philadelphia. Constants can be represented by most any symbol, similar to a proposition. Some conventions use lowercase letters, but for more natural interpretability, we can use the original noun name. The meaning of the truth symbols T and F are preserved from propositional logic. Next, let's define variables in the context of predicate logic. These are symbols that stand for an individual in a collection or set. For example, the variable x may stand for one of these days. X is Monday, or X is Tuesday, and so on and so forth. By convention, we'd normally use letters from the end of the alphabet, such as X, Y, and Z, to represent variables. A collection of objects possible for that variable is called the domain of objects. In the example above, the days in the week is the domain of the variable x. Now let's introduce predicates, which is where the name predicate logic comes from. Predicates are also referred to as propositional functions or function expressions. A predicate is a verbal statement which describes either the property of some individual, which can be a constant or a variable, or the relation between individuals. For example, we have the statement blank is human, where is human is the predicate. Down here we have relations such as blank is the teacher of blank, or blank is between blank and blank. Both of these are also predicates. Like a proposition, a predicate ultimately returns a Boolean value, either true or false. A predicate can be represented by most any symbol. Again, for natural interpretability, you can just use the original noun name. But there are other conventions that use uppercase letters as opposed to constants using lowercase letters. Now let's show how we can use a predicate to create an atomic sentence. Here, the predicate is the word likes from the sentence Finn likes chocolate. This can be represented as likes, parentheses, Finn, chocolate, where our semantic mapping ties this to the original sentence. Here's an example where the individual is a variable rather than a constant. Finn likes all food can be represented as likes Finn, x, where x is a variable. And this variable is within the domain food. Statements in predicate logic are constructed much like they are in propositional logic. In other words, by combining atomic sentences with logical connectives. Predicate logic inherits the same connectives that we learned in propositional logic. Here's our first example of a statement built in predicate logic. Our original text is, if Allison is friends with Richard, then she likes him. Here we combine two predicates with an implication. Both the predicates friends and likes describes a relationship between Allison and Richard. In this example, Allison likes Richard or chocolate. Now we're using the same predicate, but one describes a relationship between two people, and another describes a relationship between a person and food. Next, Allison doesn't like rain and snow. Here we use the negate and connectors. Now let's learn about functions in predicate logic. Recall that constants are fixed objects. It's not always concise, though, to enumerate constants for every object. Functions are similar at first glance to predicates. However, they flexibly map terms to other terms and don't require a truth assignment. For example, a function could be a mathematical function, such as the function px, which in this case is x squared. Any value given to the function p will have its value squared. However, a function could also work with objects. In other words, left leg John. This is interpreted as John's left leg. We can do this instead of specifying a constant name for John's left leg. This is a simple example to illustrate how we can save some computing effort in not having to specify both legs, but rather have a way to flexibly point to either one. Next, we're going to introduce quantifiers, a really important part of predicate logic. Quantifiers are an operator allowing more general statements that indicate how many objects have a certain property. There are two main kinds of quantifiers. First, the universal quantifier. This is represented by the following symbol. It can be read as for all, for every, for each, or for any. The main connective of a universal quantifier is the implication. Here's an example of it in use. We have the sentence, Finn eats everything that he likes. Obviously, there's a quantification here because we're using the word everything. We write this in propositional logic as follows. For all x, if Finn likes x, then Finn eats x. Differently, an existential quantifier is represented by this symbol. It means for some, there exists, there is a, or for at least one. The conjunction is the main connective of the existential quantifier. There exists some bird that doesn't fly. This is written as follows. There exists a bird and it does not fly. Another example, every person has something that they love. Here we represent that using both a universal and an existential quantifier. For all x, if there is a person x, there exists some y where x loves y. Now let's get back to that idea of a main connective. There are a couple common mistakes when using quantifiers in predicate logic. The first is using the and connective as the main connective with the universal quantifier. Here's an example. For all x, Finn likes x, and Finn eats x. This statement would be translated to Finn likes everything and eats everything, when most likely we meant Finn eats everything that he likes. It's not that we can't use this expression, we just have to be careful translating our meaning into predicate logic. Another common mistake is using the implication as the main connective with the existential quantifier. Here's an example. If there is some bird X, then X does not fly. Translating this expression into natural language can actually be very difficult, but this statement is basically only true if there is something other than a bird. What we intended to say was there exists some bird that doesn't fly. Now let's talk about the difference between a unary, binary, and n-ary predicates. A unary predicate involves properties of a single variable. Here's an example. For all x, if there's a house, then there's a physical object. In other words, every house is a physical object. A binary predicate involves the properties of two variables. Here's an example of that. For all xy, if x and y are brothers, then x and y are siblings. In other words, brothers are siblings. Ternary and n-ary predicates are also possible, where n-ary refers to predicates with more than three variables. Let's look at some other examples of sentences with quantifiers. In particular, we'll focus on some different relationships. First, let's try and capture the idea that brothers are siblings. For all x and y, if x is y's brother, then x is y's sibling. Next, let's capture the idea that the word sibling is symmetric. For all x and y, x is y's sibling if and only if y is x's sibling. Now let's express the idea that one's mother is one's female parent. In other words, we're defining mother in terms of parentage. Here we have the following expression. For all x and y, x is y's mother if and only if x is a female and x is parent to y. Now let's capture the idea that a first cousin is a child of a parent's sibling. In other words, we're going to try and define first cousin in terms of parentage and siblingship. For this, we use the following expression. For all x and y, x is first cousin to y if and only if there exists a parent and a parent's sibling, where p is parent to x, and the parent sibling is sibling to our parent. Also, the parent sibling has to be parent to y. Now that we've gotten a rough feel for what predicate logic expressions look like, let's talk about the scope of variables in an expression. The scope of a variable is the sentence to which the quantifier syntactically applies. Here's our first example. There's some x where x is a cat and for all x, x is black. The x in black x is universally quantified, but elsewhere it's not. So example, this x in cat is not universally quantified. We can interpret this expression as there is a cat that is all black. Here's another example. This time we're not going to go through explaining the entire expression, but we'll just try and examine the scope of the variables. Notice that for all x encompasses the entire expression. Therefore, the scope of for all x is the entire expression. However, the scope of there is some y only extends to the part of the expression here in parentheses. Here's a final example. Again, we see that the universal qualifier with x has the scope of the entire expression. Here, there's an existential quantifier connected to y. However, a y also exists in this part of the expression. So the scope of y includes qx of y, but since y isn't defined for px of y, this y is considered a free variable. Let's talk a little bit more about variables and what it means to be bound versus free. Variables are bound or free based on their connection to some quantifier. A bound variable is a variable in the scope of some quantifier. Variables can be given specific values as constants, or they can be constrained by quantifiers. Here's another example wherein x is bound to the universal quantifier. Also, its scope is the entire expression. A formula, in other words a well-formed formula, with no free variables is called a closed formula, a sentence, or a proposition, and it has a truth value. A free variable is any variable that is not bound by a quantifier. In order to evaluate the formula, the free variable must be replaced by an object or value. Here's another example where we have the free variable z highlighted in red. This expression is simply a formula and not a closed formula. Therefore, it cannot be assigned a truth value as of yet. Now let's discuss the difference between ground and closed formulas. A formula f is ground if it does not contain variables. For example, the predicate fish Nemo, which basically means Nemo is a fish. A formula f is closed if it does not contain free variables. Here's a couple examples. In these examples, neither is ground because they both have variables in them. However, the first is closed because it does not include any free variables. But the second example does have a free variable, therefore it is not closed. Next, let's discuss what happens when you negate quantifiers. When you negate a universal quantifier, it becomes an existential quantifier, and vice versa. Consider the sentence, "Everything is beautiful," represented by this expression. For all x, x is p. If we negate this quantifier, the sentence becomes, "Not everything is beautiful." This expression is equivalent to the existential quantifier x, negate px. Or in other words, there is some x where x is not p. We can translate this second expression in natural language by saying, there is at least something that is not beautiful. Now let's see what happens when we negate an existential quantifier. Let's start with the sentence, "It is not the case that something is beautiful," expressed by negate existential x, px. This is equivalent to the universal quantifier x, negate px. We can translate this side as everything is not beautiful or nothing is beautiful. They all mean the same thing. For reference, this transformation in the meaning of negated quantifiers is similar to what takes place with De Morgan's law. Now let's introduce the idea of uniqueness quantification. Sometimes we want to say that there is a single, unique object that satisfies a certain condition. In other words, only one. For example, there exists a unique x such that x is king is true. So let's start by thinking how we would do this using the existing operators and connectives we've learned about. These expressions show how it can be done. However, we can do this more easily using a uniqueness quantification. This can be represented with the existential quantifier and an exclamation point as a symbol. In other words, there is one x where x is king. Let's try this out in another sentence. Every country has exactly one ruler. For all C, if C is a country, then there exists one R where R is ruler of C. There's also something called the iota operator. It's represented by this symbol. This expression means that the unique x such that px is true. In other words, to say the unique ruler of Fredonia is dead, we could use the following expression. In the last slide, we saw the equals sign come into play, so let's go into it in more detail here. Equality is not strictly the same thing as equivalence, although they're conceptually related, and neither means the same thing as the biconditional connective. Equality, represented by the equals sign, indicates that two terms refer to the same object. For example, consider the function father parentheses John, which might have the meaning John's father. If we use this expression, we're saying that John's father is the same individual as Henry. In other words, this function refers to the same object as the constant Henry. Using equality, let's try and convey that Richard has at least two brothers. We can do that with this formula. There is some x and y, where x is Richard's brother, and y is Richard's brother, and x does not equal y. This last part ensures that x and y cannot be the same brother, meaning that Richard has at least two brothers, but not exactly two brothers. Let's revisit the rules of precedence with connectors. We now need to consider the universal and existential quantifiers and their precedence. Both have a higher precedence than all other logical operators or connectives from propositional calculus. So now the precedence starts with these quantifiers and then continues in the same order as the connectives in predicate logic, starting with the negate, and, or, implies, and biconditional. Again, similar to propositional logic, we can use parentheses to disambiguate precedence when needed. Let's go through some examples where we translate natural language to predicate logic formulas. Every gardener likes the sun. For all x, if x is a gardener, then x likes the sun. You can fool some of the people all of the time. Here we have for some x and all y, if there is a person x, and a time y, those x people can be fooled all of the time. Now let's try, you can fool all of the people some of the time. The meaning of this sentence can be captured equivalently using both of these expressions. Here's another example. All purple mushrooms are poisonous. Here we have for all x, if x is a mushroom and it's purple, then x is poisonous. How about no purple mushroom is poisonous? We can also write this one in a couple of ways that are equivalent. Either we can use a negated existential quantifier or the universal quantifier. But we have to restructure the expression based on which one we're going with. The first one says there's no x, where x is purple, a mushroom, and poisonous. Another example, there are exactly 2 purple mushrooms. This is related to an example we gave a couple slides back where we tried to quantify having at least 2 brothers. But now we're trying to quantify exactly 2. We can see this expression gets a little complex. Notice that we'll need equality in order to complete this. Similar to propositional logic, now we're going to dive into predicate logic equivalence. First off, you'll be relieved to know that all logical equivalences we defined in propositional logic still hold here in first-order logic. However, there are some additional rules for formulas containing quantifiers. First, let's take a moment to define equivalence in the context of first-order logic. Statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value no matter which predicates are substituted into these statements, and no matter which domain of discourse is used for the variables in these propositional functions. The domain of discourse basically refers to the universe of possibilities. So a simple way of putting this is that 2 things are equivalent if they always give you the same truth values no matter the context. Let's take a look at how you can go about using the previous propositional equivalences that we already learned. Here we look at applying propositional equivalence outside a propositional function that includes a quantifier. For example, we have a quantifier here within parentheses with 2 negates on the outside. We could still apply the double negation here. In other words, this is equivalent to this. This also works within inside the scope of a quantifier, such that the double negate here is equivalent to this. Again, inside the scope of a quantifier, we're going to apply contraposition. Notice that the scope of both x and y includes everything within parentheses, and we use contraposition to change this expression to this one. Note that the respective variable and predicates stay together during this transformation. However, be careful not to assume that all of the predicate equivalences you've already learned can be applied in this same way. The following slides will show some exceptions that include quantifiers. Here are some basic equivalence rules involving quantifiers. Formulas are logically equivalent if they differ in some of the following ways. The name of the variables in the scope of quantifiers. X is replaced here with y. After all, the name itself doesn't really have any meaning. It is the domain of the respective variable that is the important difference. Formulas are also equivalent if they differ in the addition or elimination of quantifiers whose variable does not occur in their scope. For example, for all x, p of x is equivalent to p of y. Formulas are also logically equivalent if they differ in the order of quantifiers of the same kind. In other words, nested quantifiers. Here we have 2 universal quantifiers attached to x and y, and p of xy. This is equivalent to universal quantifier y, universal quantifier x, p of xy. This can also be written using a single universal quantifier and y, x, or x, y. Let's explore the equivalence of nested quantifiers using some natural language. We just saw this example in the last slide. Let's create a more specific expression. For all x and for all y, x loves y, is equivalent for all y and for all x, x loves y. Either of these can be translated as everyone in the world loves everyone in the world. Here's another example where we've just shifted the order of x and y connected to existential quantifiers. This statement translates to at least one person in the world loves at least one other person in the world. However, now we're introduced to an important exception. For all x and for some y, px of y, is not the same as for all y and some x, px of y. Let's look at example translations to understand why. The first example translates to everyone in the world loves at least one person. That's because of how we interpret the loves xy and the importance of the order of where x and y occurs. The second expression translates to at least one person loves everyone in the world. Let's look again at negated quantification and equivalence. We already saw these two examples earlier that were derived from De Morgan's law. The negation of the universal becomes the existential, and the negation of the existential becomes the universal. Note that the predicate also flips in terms of negation. The first expression can be translated as someone doesn't love Finn, and the second, everyone doesn't love Finn. Here are some other related equalities. No one loves Finn, everyone loves Finn, and someone loves Finn. Let's look at some other equivalences with quantifiers. This first one deals with conjunctions. In this first example, we have a universal quantifier with a conjunction between two predicates on the inside. This is equivalent to applying the universal quantifier independently on either side of the conjunction. This phrase could translate to all things are and were. In this example, we have an existential quantifier and the or symbol. Given this combination, we can do something similar, where the existential quantifier is now applied independently to either side of the or symbol. This expression could be translated as some things are or were. However, you can't do this if you have a universal quantifier and an or. Nor can you do this if you have an existential quantifier and an and. Now let's jump into predicate logic semantics. First, let's talk about interpretations versus models. In predicate logic, an interpretation specifies, assigns, and instantiates the meaning and values of a formula's signature given a domain. The signature includes all non-logical symbols, including predicates, constants, and functions. This is basically laying the groundwork for how we'll interpret truth from predicate logic statements. By applying an interpretation to a signature, we basically yield a proposition with a corresponding truth value. Here, a model is an interpretation that satisfies a sentence. Let's define the domain of predicate variables. The domain, given by this symbol, is a set of all possible values that the variable may take. For example, the domain could be a set of integer values 1 through 4, or the domain could be the set of all real numbers. Importantly, each unique predicate variable may have different domains. Here's an example. Given that px of y means x is greater than y, and the domain is all integers, we could try out some instantiations such as p, 4, and 3, given that these are both integers. This can be interpreted as 4 is greater than 3, which is true. Another instantiation is p, 1, and 2. This means 1 is greater than 2, so this is assigned false. You can also explicitly define the domain of a variable within a formula. This is called conditional quantification, and it looks something like this. When the variable is defined, for instance next to a universal quantifier, we can use this symbol to attach it to a domain. In this case, the domain is the set of all real numbers. Remember that an instantiated predicate is basically a proposition, where the underlying variables in the predicates are evaluated with specific values. Let's take a moment to define sets. A set is a well-defined collection of objects. The elements of a set, or members, can be anything, including numbers, peoples, letters of the alphabet, other sets, etc. Sets A and B are equal if and only if they have precisely the same elements. Sets are really abstract objects. They don't occupy time or space or have causal powers, even if their members do. So what is substitution in the context of first-order logic? This is the replacement of a formula's signature with objects or values from the domain. Basically, we're taking a variable and giving it a value. This is an important part of determining formula truth, which is needed for inference in first-order logic. Here's a quick example. If we have the following formula, for all x, if x is a fish, then x can swim. Let's now substitute x with the value of Nemo. To determine if Nemo can swim, we must replace every occurrence of the variable x in the implication by the term Nemo, an object from the real world. This gives us, for all x, if Nemo is a fish, then Nemo can swim. Now we can evaluate the truth. Formally, substitution takes place within each atomic sentence, and it only applies to free variables within each atomic sentence. To do this, we have to ignore bindings from the sentence as a whole to determine free variables. The annotation for substitution is formally denoted here by fish bracket Nemo/x, indicating that we've given x the value of Nemo. Quantifiers as conjunctions and disjunctions. If the domain is finite, then universal or extensional quantifiers can be expressed by conjunctions or disjunctions. In other words, if our domain includes the integers 1 through 4, then we can express this universal quantifier as a series of conjunctions. Each clause in the conjunction is simply the predicate substituted with a value from the domain. So here we have P1, P2, P3, and P4. We can do a similar thing with existential quantifiers. However, these are connected with disjunctions, or ORs. If the domains are infinite, the equivalent expressions without quantifiers will be infinitely long. This property is helpful when considering sentence truthfulness. For instance, consider this example. P of x is equal to x squared less than 10. We can convert this to a set of conjunctions. Let's assume that our domain is the same as in the above example. That means that this x squared less than 10 would be applied at each of these locations. For x of 1, our formula would be 1 is less than 10, which is true, so this value is true. 2 to the power of 2 is 4, so this is also true. 3 to the power of 2 is 9, so this is also true. And lastly, 4 to the power of 2 is 16, which is not less than 10, making this false. This entire expression would then resolve to false, because they're not all true. However, if the domain was 1 through 3, we intuitively know that this would resolve to true, because 1 through 3 each become true. Now let's formally define sentence satisfiability for first-order logic. A sentence in predicate calculus is satisfiable if and only if it is true for some domain and some propositional function substituted for the predicates in the sentence. An element, for example x, that makes a sentence false is called a counterexample. Here's an instance of a satisfiable formula. Here's an unsatisfiable formula similar to one that we've seen in propositional logic. Here we have an AND connecting P of x and not P of x. Therefore, this can never be true. Next, let's formally define sentence validity. A sentence in predicate calculus is valid if it is true in every interpretation. In other words, if and only if it is true for all domains and every propositional function substituted for the predicates in the sentence. Or in other words, it is true for all rows of the truth table. Valid sentences in predicate logic play a similar role to tautologies in propositional logic. However, they're referred to here as first-order validity. Briefly recall from propositional logic the concepts of valid, contingent, and unsatisfiable. Remember that a tautology was an abstract proposition that was always true, and our truth table had true values for every model or interpretation. A first-order predicate logic sentence is first-order valid if it is satisfied for every interpretation. This is similar to the idea of the tautology. Here are some examples of first-order valid formulas. For example, if for all px, then there is some x px. Or for all x px, there is some pc where c is a constant. Or if pc, then there is some x px. Let's see what's required for truth in quantified statements. Let's start with the universal quantifier, where x has the domain D, and we have the predicate px. This universally quantified predicate is true whenever px is true for every x. It's therefore false when there is just one x for which px is false. Shifting to the existential quantifier, this is true when there is even just one x for which px is true. And it's only false in the situation where px is false for every single x, because all you need is one to be true. Let's extend this thinking now to quantifications including two variables. Let's start with two universal quantifiers. In this case, these universal quantifiers with two variables are true when pxy is true for every single pair of x's and y's. It can be false if there is just one pair x and y for which pxy is false. How about for this situation, where we have both a universal and an existential quantifier? This is true when for every x, there is at least one y for which pxy is true. And it's false if there is an x such that pxy is false for every single y. When we have the existential quantifier first, this formula is true when there is at least one x for which pxy is true for every single y. And it's only false if for every single x there is at least one y for which pxy is false. Lastly, let's look at the example where we only have the existential quantifier. This is true if there's at least one pair of x and y for which pxy is true. And it's false if pxy is false for every single pair of x and y. I encourage you to take some time to think through all of these examples. Now we ask the question, how do we go about determining truth values? Today we're going to cover three systematic approaches. First, the method of exhaustion, then the method of case, and finally the method of logical derivation. We can use the method of exhaustion if the domain contains a small number of elements, and it's reasonable to try them all. So let's say we have the domain that includes these 5 integers, and we have the following formula. There's some x with the domain D, and x squared equals x. And we want to find out if this statement is true or false. We can determine truth by checking and substituting in every single value in this domain. When we check all of these numbers using the equation x squared is x, we find that they're all false. Therefore, we've determined that this formula is false given the domain. What's the limitation of this method by exhaustion? Well, this can be impractical if your domain is really large, so it might not be efficient to check all of your options. For example, what if the domain included all integers? So our realization from that last example is that we can't hope to exhaustively search a domain. So now let's check out the method of case for determining truth. Here, we can use positive examples to prove an existential quantification. For example, let Z be the domain of all integers. And our formula is, there is some x with x's domain being Z, where x squared equals x. Well, in this example, with a little intuition, we can try out 0 or 1, and in both of these, the answer is true. Therefore, because this is an existential quantification, we've proven this formula to be true given the domain. In a related way, you can use a counterexample to disprove universal quantification. For example, let's say that R denotes all real values, and we have the formula for all x in the domain R, x squared is greater than x. Let's try out the value x is 0.3. This will end up being false and therefore give us a counterexample. This allows us to disprove this formula. Importantly, a positive example is not a proof of universal quantification. So for instance, if we had tried a value of x is 3 here and gotten a true value, it doesn't prove this formula to be true. Also importantly, a negative example is not disproof of an existential quantification. It may be hard to find suitable cases to prove or disprove some of these examples, even if such a case does exist. The method of case is pretty impractical in a lot of situations, but can come in handy sometimes. Lastly, we have the method of logical derivation. This method consists of using logical steps to transform one logical expression into another. As a really simple example of this, let's start by considering an arbitrary domain with n members. And we'll ask the question, is this formula logically equivalent to this formula? Note that they're pretty similar. Starting with the first formula, recall that we can take an existential quantifier expression and turn it into a set of disjunctions. With a little bit of transformation, we can demonstrate through logical derivation that the one formula is equivalent to the other. This is similar to the equivalence proofs we conducted in propositional logic. We'll end this lecture by briefly mentioning the undecidability of satisfiability and validity. Basically, in first-order logic, there does not exist any algorithm, no computer program, that can decide whether a first-order predicate logic sentence is satisfiable. In other words, an algorithm that will take an input sentence G and output yes if G is satisfiable and no if it's not satisfiable. This should sound familiar from our discussion of history and Alan Turing's work, where he proved that there is no computer program that decides whether a given computer program P halts for a given input number n. This is called the undecidability of the halting problem. Let's review what we covered in today's lecture. First, we defined predicate logic. Then we covered the new predicate logic syntax, including constants, variables, predicates themselves, functions, equality, quantifiers, the difference between bound and free variables, and we looked at some examples of translating from natural text to first-order logic. We also covered predicate logic equivalence, and examined how equivalence differs between propositional and first-order logic. We also focused a lot on universal and existential quantifiers and how they impact equivalence. Lastly, we covered predicate logic semantics, specifically interpretations and models, satisfiability, validity, and truthfulness. And we took a brief look at how to determine truth in first-order logic. Here's today's quote. God is represented as infinite, eternal, incomprehensible. He is contained under every predicate in non that the logic of ignorance could fabricate. Just a reminder that assignment 2 is available on Canvas and will be due after the second module. The specific due date is available on the course syllabus. Thank you very much for your attention, and I'll see you next lecture.